You are looking at the deepest image ever captured of a single target in the universe by the James Webb Space Telescope. The focus of this record-breaking observation is Abel S1063, a massive galaxy cluster located about 4.5 billion light-years away in the southern sky, in the constellation Grus, the Crane. At first, Abel S1063 may seem like just a large gathering of galaxies, but it's much more than that. This cluster contains thousands of galaxies packed into a relatively small region of space. Its extreme mass makes it a powerful cosmic lens, bending and magnifying the light from even more distant galaxies behind it, a phenomenon called gravitational lensing. To capture this image, Webb observed Abel S1063 for an incredible 120 hours, its longest exposure on a single target so far. Instead of one photo, this image is made from 9 different exposures taken at various near-infrared wavelengths using Webb's near-infrared camera. These exposures were combined to gather as much light as possible and bring out the faintest and most distant galaxies ever seen. This isn't the first time astronomers have studied this galaxy cluster. In 2016, the Hubble Space Telescope observed it as part of the Frontier Fields program, revealing arcs and smears of distant galaxies created by the cluster's lensing power. But now, Webb has taken this to an entirely new level. Its advanced infrared vision reveals more galaxies than ever before, many from the early universe, and shows them in far greater detail. Abel S1063 is a gigantic cluster of galaxies, all bound together by gravity. But that's not the whole story. Surrounding this cluster is something we can't see directly, dark matter. While it doesn't emit or reflect light, we know dark matter is there because of the way it distorts the space around it. It's this invisible mass that plays a key role in one of the most fascinating phenomena in astronomy, gravitational lensing. At the heart of Abel S1063, you'll see bright, beautiful galaxies. But look more closely, and you'll notice something even more remarkable: faint, stretched arcs of light curving around the cluster. These glowing arcs are not part of the cluster itself. They are actually background galaxies, so distant that their light has traveled billions of years to reach us. As that ancient light passed near Abel S1063, the cluster's immense gravity bent it, just as Einstein predicted with his theory of general relativity. Massive objects, like galaxy clusters, can warp the fabric of space, causing light to follow curved paths. It's like looking through a giant magnifying glass in space. This image is what's known as a deep field, a long exposure of a single area of the sky. The idea of deep fields has transformed our understanding of the universe long before the James Webb Space Telescope came into the picture. This groundbreaking approach began with the Hubble Space Telescope in the 1990s. In 1995, Hubble captured the famous deep field north, staring at a tiny, seemingly empty patch of sky for over 100 hours across 10 days. To everyone's surprise, it revealed nearly 3,000 galaxies, many from a time when the universe was still very young and galaxies were just beginning to form. This single image proved that the empty parts of the sky were anything but empty. They were filled with ancient galaxies. This was just the beginning. In 2004, Hubble went deeper with the ultra-deep field, capturing the most distant galaxies ever seen at that time. These galaxies likely formed just a few 100 million years after the Big Bang, emerging from what astronomers call the universe's dark ages. Later efforts, like the Hubble Extreme Deep Field and the Frontier Fields program, which included galaxy clusters like Abel S1063, pushed the limits even further by using gravitational lensing to magnify the light from background galaxies. The idea behind deep fields is both simple and powerful. The longer you look, the more light you collect. And with more light, you can detect fainter and more distant objects, some so far away that their light has taken over 13 billion years to reach us. Looking at a deep field isn't just gazing into space, it's looking back in time. That's because light doesn't travel instantly. It takes time to move across the vastness of the universe. So when JWST observes galaxies that are billions of light years away, the light it's capturing left those galaxies billions of years ago. We're not seeing them as they are today. We're seeing them as they were when that light first began its journey. It's like looking at a cosmic time capsule, the universe's ancient history, frozen in light. This deep observation of Abel S1063 is part of a larger effort known as the GLIMPSE program, an ambitious initiative using the James Webb Space Telescope to study one of the most important chapters in cosmic history, the cosmic dawn. This is the era, just a few million years after the Big Bang, when the very first galaxies and stars began to form. By focusing Webb's powerful infrared eyes on this single region for 120 hours, the glimpse survey has pushed the boundaries of how far back we can see. In this deep field, astronomers have identified galaxies at extreme redshifts, possibly even beyond 15. For context, the current record holder is GNZ14, a galaxy detected at Z equals 14.44, which formed just 280 million years after the Big Bang. If these new candidates are confirmed, they would mark an even earlier time in the universe, bringing us closer to witnessing the birth of the very first galaxies. Webb's deep observations of Abel S1063 and other regions of the early universe have discovered something truly unexpected. A population of galaxies that formed far earlier and grew much faster than current theories predict. Some of these galaxies, seen less than a billion years after the Big Bang, are already nearly as massive as a Milky Way. This has come as a surprise to scientists and is now seen as a serious challenge to our current understanding of how galaxies form and evolve. According to standard cosmological models, galaxy formation in the early universe should have been a slow and gradual process. These models suggest that early galaxies could convert only up to 20% of the gas in their dark matter halos into stars. But the ultramassive galaxies observed by Webb seem to have defied those rules. They managed to turn much more of their gas into stars, and did so very quickly. This unexpected efficiency has become known as the efficiency paradox. To explain how these galaxies grew so large, so fast, scientists are now rethinking many of the processes believed to govern the early universe. Perhaps the gas in these galaxies was denser than we thought. Maybe it cooled faster or interacted with dark matter in unexpected ways. Whatever the reasons, it's clear that our existing models need to be updated to reflect these observations. Adding to the puzzle, some of these early galaxies also contain heavy elements like nitrogen and oxygen, which can only be created in stars. Their presence suggests that not only did massive stars form quickly, but they also lived and died fast enough to enrich their surroundings with new elements. That means multiple generations of stars must have already come and gone in just a few 100 million years. Another groundbreaking insight from the James Webb Space Telescope's deep field observations concerns a major turning point in cosmic history, the epoch of Reionization. This was the era when the universe emerged from its dark ages, a time when cold, neutral hydrogen filled space and made it opaque to light, becoming the clear, transparent cosmos we see today. This dramatic transformation was powered by the first stars and galaxies, whose intense light reionized the hydrogen, allowing light to travel freely across the universe. Until now, astronomers believe that large galaxies or super-bright objects like quasars were the main drivers of this transformation. But Webb has turned that idea on its head. Its observations reveal that dwarf galaxies, small, faint galaxies that formed early, were likely the true heroes of reionization. Despite their tiny size, these galaxies produce 4 times more ionizing radiation than expected. That makes them incredibly efficient at blasting away the hydrogen fog that once cloaked the universe. The key lies not in their individual brightness, but in their numbers. There were simply so many of these little galaxies that their combined output was powerful enough to reshape the entire universe. This shift of focus from a few bright beacons to a collective glow from countless faint sources, each playing a vital role in lighting up the cosmos. Evidence for this comes from galaxies like Jade's GSZ13-1, observed at a redshift of 13, which already shows signs of existing in a fully ionized region. This tells us that the reionization process may have started earlier than previously believed, and that these early galaxies were especially good at reheating the universe with their energetic radiation. These findings are dramatically changing how scientists understand the cosmic dawn, the period between 50 million and 1 billion years after the Big Bang, when the first stars, galaxies, and black holes appeared. JWST's data suggests that reionization likely began around a redshift of 8.9, and that early galaxies formed and evolved much faster than our models had predicted. These groundbreaking discoveries aren't the final word. They are just the beginning of a new chapter in our exploration of the cosmos. From Hubble's early deep-field images to Webb's stunning breakthroughs, each step has built on the one before it. And when new data challenges what we thought we knew, it doesn't signal failure. It drives science forward. This is the heart of cosmology, a constantly evolving dialogue between observation and theory. Each unexpected finding forces scientists to ask new questions, refine old models, and explore fresh ideas. It's a reminder that science isn't a fixed set of answers. It's a living, self-correcting process. And with every new image from the James Webb Space Telescope, we're not just seeing farther into space, we're pushing the frontier of human understanding. So, thanks for watching. If you enjoyed this video, don't forget to give it a like and subscribe to our channel for more journeys into the universe. And if you haven't seen it yet, NASA recently released the most breathtaking images of Jupiter we've ever seen. You won't want to miss that. Click here to watch the episode now.